integrated circuit 2, transistor characteristic. Now we look at the transistor more quantitatively. We need to know how to calculate the current and voltage and stuff to do the analog design. And digital design, you also need to understand what it is, but more emphasis on the logic design. Okay, so we have a collector, emitter, and the base. So we have a IB, base current, and IC. We apply VCE and VBE. Okay, so what's happened is there is a transistor characteristic factor alpha. Alpha is a ratio of IC and IE. That means IC and IE is different by IB, right? So beta is defined by IC over IB, because IC equal the IE equals IC plus IB. Both current, this and this together will be IE, right? So the beta is alpha over 1 over alpha. It's like, say beta is 100 typically. Okay. What does this mean? That means you have a ICE, the current, and you have IB. So IB kind of determine what kind of ICE you get. Okay, if you increase IB, ICE increase regardless the voltage. Okay, now of course the cutoff point, this below certain IB, no more IC. And another characteristic is VCE. When the VCE, this voltage get lower below VBE, this is like VBE. So this voltage, can you see this? If VCE become below VEE, then characteristics start changing to like a diode. So it's a saturation point. This range is saturation point. The above saturation point is normal transistor operating range, which is IB determine ICE. So doesn't matter how much voltage you apply, this guy determine this guy. So if you have a V, then this I is determined, so voltage is Ri, right? Because I is determined by this guy. Okay, so transistor's normal operating range, which is this range, is like model is IB going through the diode. Okay, IB increase as VBE increase. Okay, so this side is like a current sink, right? IC, it's a beta IB. So IC is a function of IB. So this is kind of a transistor model. Okay, and alternative current is going to be like this model. It's going to be beta delta VBE. Sorry, this is current, not the voltage. Okay, so that's a bipolar transistor model. How about MOS? The MOS has a source and drain. They use a different terminology, and the gate. And since this is oxide silicate, it's an insulator. There's no current. Ig is almost zero, right? So it's a high impedance input. And transistor characteristic pretty much same. Even you give ISD, no matter how much voltage you give, IS is pretty much depend on VG. So it's a voltage driven the current, this transistor, okay? And here the same thing as saturation area and cutoff area. So VG, when you increase VG, IS increase regardless. So even NMOS, if you make circuit like this, so this VG determine this IS. So this voltage is the function of this guy. Okay, that's the way transistor operate. The transistor model, the same way. In this case, there's no diode. This is infinite, very high impedance input, and GM is same as the gain of the transistor and the VG. Okay, the YGM is translated to I, so it's going to be GM is going to be 1 ohm dimension. So VG is translated into this IS. Okay, that's gonna be the transistor model. So MOS or bipolar, it has a similar characteristic. Input dictate how much current go through the transistor. Okay, this how much current goes through the transistor determined by bipolar transistor IB, the current, but MOS VG, the voltage. Okay, so as long as the characteristic of transistors, the difference is as long as it's a transistor, it's very similar. It's just current driven or voltage driven. That's the way you remember, right? That's the difference between bipolar and the MOS. And analog circuit, mostly bipolar transistor, and analog circuit is established very well using bipolar transistor, and it's need to control various things like a current and resistors and stuff. So it's pretty hard to do by MOS. Okay, digital circuit is lost because the primary reason is it's lower power, and you need a lot of gates, a lot of transistor on a single chip. You don't want to have a higher power transistor. Okay, but extremely high speed is still used bipolar because it's burn the power to speed up. Okay, here's a digital circuit example. This is called TTL, transistor logic, and has a multi-emitter, and show you how to make a multi-emitter later. And you connect like that. So what's happened is when one of them pull down, then this transistor become on. So this voltage drop, then this becomes high because this current becomes zero. That dictate this voltage, right? So it's an AND, opposite polarity. One of them goes low, then it's become high. Okay, and this resistor, how you make a resistor on a silicon chip? You cannot make capacitor or inductors. Inductance and capacitors are impossible to make on a silicon chip. But resistor we can make. This resistor, the N well, we tap into this here, and this is a resistor, but it has to be surrounded by opposite polarity. So the resistor is higher voltage, this P wall going to be grounded, so it's like opposite polarity diode. Okay, and this is R. The Cmos, you use PMOS and NMOS, so you can make the gate. Now what's happened is Cmos, when this side is on, this side is off. If this is on, then this side is off. So after switching the logic 0 and 1, both sides, the current is 0. The current increases only during transition of the gate. So it's very dynamic power consumption. And this dynamic power consumption is consumed by those parasitic capacitor around. The capacitor has to be charged and discharged. That's where the power is used. Same as TTL. But TTL, beside that, there is a constantly running current. That's why the TTL is higher power. When you have millions of transistors, then bipolars become too much power. So CMOS is low power, because as long as it's not switching, it's zero consumption of power. Okay, the CMOS was in the beginning it's large size, and until it's miniaturized, it wasn't really a viable candidate for making an IC chip. Now after miniaturized, speed get faster, so switching speed is as fast as the bipolar and lower power, so it became the choice. CMOS became the choice of all the LSI, large scale integrated circuit. Okay, so but bipolar still used for analog circuit and higher speed, extremely higher speed, like ECL, emitter coupled logic, and this is for communication device. It requires very fast speed, and bipolar is the way to go. Okay. Now another things we have to know is Shockley diode equation. The Shockley is the Dr. Shockley moved from East Coast to Silicon Valley and started the company that make the initial diode and transistor. Okay, and that was the beginning of Silicon Valley. Now he determined the IE, the current IE, is a constant e to the VBE over VT. VT is temperature function, Boltzmann's constant, and the electron charge, and VBE minus 1. Okay, so basically it's like a diode, VBE, but IE for transistor is not just diode. This current is going to be multiplied by beta, so the IE, the IC is going to be beta IB. Okay, so this is the basic equation. It's exponent function, and this is very important to understand in analog design. Okay, because when you have a transistor, pretty much this voltage change from 0 to VBE, which is about 0.628, the highest, and some low VEE devices 0.4. So that's the only range it's change. But this voltage change swing any way you like, even 20 voltage is change. Okay, that's become very important point. And also beta is a function of temperature T, and also the temperature compensation become very big issue in the IC chip design, and this will come out later when we start getting into the details of analog design and digital design. Okay, so if you like this video, hit subscribe.